we've got a couple of presentations from Steve, one on hardware and one on software, with a little bit of Q&A after each of those. And this is sort of part of the Arduino environment that Steve's been telling us about on and off over the last few months. And this is a bit of a revisit, I think, isn't it, Steve, to the
Yeah.
PCF8575 input-output expander?
Yeah, we had a quick look at it when we were doing the plank, and but we only looked at it very, very briefly as part of the whole project, not as a standalone item. Um, Basically, if I can, okay, this is a PCF 8575, 16 bits, and both inputs and outputs that can work basically together with each other. Um, 8575, yeah. We can see here that we've got there's a library for this, which we're using, which is the Rob Tillart library, which is on GitHub. If we've got time, we can have a quick look at that later. But basically, the library covers virtually everything we want. Unfortunately, his examples are not great, and there's a couple of gotchas in it because he's missed off. Again, it's the usual thing where there's been an update and he's updated his library, but not updated his examples. But not to worry, because the software which I've got here has those updates in it. So basically, if I just go through this quite quickly, if we start at this end here, we've got our ground, which is common throughout, a VCC, which is what's coming from the device that we're using it. So this can either be an ESP32 or it can be an Arduino. If it's ESP32, VCC is going to be at 3.3 volts. If it's an Arduino, it's going to be at 5 volts. We can manage with that, not a problem. I'll come to that in a minute. We've got our I2C data. I2C is, we were talking about it when we first started off. I2C is definitely here to stay. There's so much if we're looking at the ESP32 line and also the Arduino, or the whole environment. So many devices are using I2C. We can't really ignore them. But we do have the limitations, certainly with interference that we've noticed. We have to find a way around that because virtually every display now that we would ever use is using I2C. We have the PCA9685, which is like a really standard module, so we have to work our way around it. But we've got here a thing called interrupt. Now, interrupt is a really nice feature which tells us when one of the pins has changed value, but I'm not going to go into that at this moment in time. We can talk about it later for anyone that really wants to know about it. It is quite useful to be able to use it, but we're not going to use it in this particular example. So we have here our ground pin, and this ground pin, and that ground pin are all connected together. So there's no real problems with any of those. We've got VDD here. Notice it's not VCC. I'm going to mention VDD in a minute, but basically this is the voltage at which our inputs and outputs are going to be referenced to. So that can either be 3 volts, 3.3 volts, particularly in the event of an ESP32, or it can be 5 volts if we're using a conventional Arduino. And then we have our ports. We've got a port 0, pin 0, and port 0, pin 1, and it goes all the way up to port 0, pin 7 here. Now, a little bit of a gotcha, which I noticed, which didn't really help from my point of view, was that it then goes to port 1, 0. So it's port 1, input 0. That's not port 10 or input 10. So it starts at port 1, 0, port 1, 1, port 1, 2. So as they go up in that direction, so from right to left, they go high. Here it goes from left to right, they go high. And again, that sort of is easy to catch you out if you don't notice it. But again, we've got VDD. Both these VDDs are connected together. Both these grounds are connected together. Basically, that's it on the board. We've got the main chip there, and we've got this linear power supply, which basically what it's doing is it takes the VCC and as an input, and then it takes the output at 3.3 volts to VDD. And that's the way that is hardwired into the system. So even if we're using a 5 volt VCC, we're going to get 3.3 volts on our inputs and outputs. Now that might be a problem. Sometimes it's really useful to be able to do that because we're using 3.3 volt devices, but we need to be wary of the fact that it's no longer 5 volt. So if we put something 5 volt in, we could start doing damage to things. If we look at the back of this, we can see here, turn it the right way around, so you can see. we have a bridge here which bridges VCC and VDD. In effect, what that does is short out that input and output to that regulator. So what that does then is it forces the output of the device that we're feeding it with, the VCC, and puts VCC now on VDD, or puts VCC on VDD. So this now, in the case of an Arduino, would work at 5 volts. In the case of an ESP32, it would be running at 3.3 volts. That's really important because if we put an Arduino, an ESP32 in, and we don't short those inputs out, this is going to try and drop the 3.3 down to 3.3, which you can't do. If we get 2 volts out of it, we'll be lucky, but either way, it's going to be really unstable. So we might get it to work, and it might appear that it's going to working, but as soon as we start loading this up, we're going to get all sorts of drift and all sorts of problems with it. So the long and the short of it is, unless there's a very good reason why you need to shift levels, always bridge that out with a solder bridge. So that basically is like a number one, a must do, unless there's a good reason to not do that. Other things to note here is we can select which, it's all I2C, and it allows us to put in 8 values of addresses in. And these are A1, A0, and A2. These are, I said that the wrong way around, but never mind. These basically are binary. We added together binary like we do with virtually other things. But in this situation here, we have to either, the center pin is the A0, A1, and A2. And then we either have to ground it or connect it to VDD. Now, we've got to choose one or the other. We can't leave them floating. In the past, we have tried leaving them floating, and I've noticed that all of a sudden the I2C address will suddenly change for no apparent reason. And this is why, because they can't cope with being floated. So if we want to set this at OX hex 20, which is the lowest address, we have to ground all of these with the bridge, solder bridge. If we want it to be OX21, we would then bridge VDD for the first one and then ground for the other 2, and so on. But in a similar way that we would do the same with the PCA9685, that's the servo driver or the PWM for LEDs. So it's slightly different in that it's a single link on this, but on these we have to put the 2 links in. We have to tell it there is no pull-up resistors in those. So that basically is the chip. So once we've done that to our chip, what we end up with, you can see on this one here, you can see the solder links that we've got in here. So we've got that grounded, that one grounded, and that one grounded, and you can see all those, the VDDs are not connected. So this is now working at address OX20. And also here, we've got the VCC and VDD pin. So what I'm going to do with this now here, can I change my camera over? It's what else the pins can be. No, actually, before we do that, let's the pins can be both inputs and outputs. And the reason this works is because, unlike an ordinary Arduino, where the input is pulled up, if we wanted to use, say, an open circuit switch or something like that on it. This doesn't need us to define an input or an output. They're both working the same way. So in effect, we can write or we can read any pin at any time. If we want it to be an input, all we need to do is to write a 1 to the output, which pulls it up high. Now, it's not a hard high, it's a resistive high. There's like a resistor, a pull-up resistor when we make it go high. So that when we tell it to go to 0, even though we've already told it to go to 1, it will then literally ignore that resistor. It will do, well, it'll just bypass the resistor. It's like any other pull-up resistor. So if we were to, say, short out a pin as an input, even though we've written a 1 to it, because there's a resistor behind that, it will allow us to do that. It won't overload anything. The disadvantage is if we are using an input, say, from another device, such as, I don't know, we might have another Arduino or an ESP32 or something else, or even a sensor, which is sending 5 volts as a 1. But if we then turn around and write by accident 0 to that, we're going to short out that sensor and we're going to get the magic smoke. because its ability to short out is very much greater than its ability to be able to pull up to pull high. So everything needs to be referenced to 0. So in effect, what we're doing here, in order to use it as a switch or an input device, we're shorting out the input. If we want to use it as an output device to make it go high, we turn it to 0. So it's all the 0 side of the line that we're doing. If we need it to go high with a 1, we would need to use a transistor. Transistors never, or a MOSFET. Transistors are probably not a bad idea anyway, or MOSFETs, because we can get more power with it. But again, it depends on the application. Sometimes we would need to do that sometimes. We get about 25 milliamps per output on this, which is enough for an LED, but we've only got a total of 100 milliamps for the whole board. So if we decide we've got to have 16 outputs, we can't realistically run that many LEDs at the same time. So that takes care of that one.